Okay, so let's see what you remember from yesterday. Okay, this one is not one of the hardest ones for sure. Okay, you do have to read it carefully though to make sure that you get all the contextual clues that are part of driving a car off a cliff, which, in case it's not clear, that is not a good idea. Okay, we should definitely not go driving cars off cliffs, okay, because it's kind of dangerous. Okay, I'll give you a few minutes to see if you can get that. Okay, just in case you're having trouble getting started, okay, this is the situation we're dealing with. Okay, we got the car going off of the cliff, so it'll do this. Okay, crash down here. Alright, it's upside down. Okay, so here, VF is 53 meters per second, okay, and this would be also where the final height would be what number? 0, crashes into the ground. Okay, up here, we don't know what the initial height is. That's what the question wants us to calculate, but we do know that the car was driven off at 25 meters per second. Okay. So there's no mention of work or any forces or anything like that, so we can assume that the initial energy equals the final mechanical energy. Okay? So again, we expand that out like we always do. That means initial potential plus initial kinetic equals final potential plus final kinetic. Are any of those 0? Which one? Yeah, the height final, okay? Because height final is 0, this is 0 because we have to multiply height final in that one. So it has no potential energy final because its final position is ground level. Okay, what I'm looking for is the initial height. That would be part of that term. So I need to get that term by itself before I start plugging in other formulas. What do I do with EKI to move it to the other side? Subtract it. All right, so the initial potential is going to equal the final kinetic minus the initial kinetic. Okay, now I can plug in my formulas. M times G times H initial equals 1/2 mv final squared minus 1/2 mv initial squared. Did I ever tell you M? Why not? Doesn't matter. Cancels. Okay, if you don't like canceling it, put in whatever number you want. Okay, it really makes no difference. You could put in 1 kilogram, you could put in 250 million kilograms, it won't make any difference. Okay, but whatever you're comfortable with. Okay, all right, so I'm going to cancel off all of the m's because it's in every term. Okay, I'm just looking for HI. What do I do with G? Divide it over to the other side. All right, so there's my formula. Okay, so I'm going to go 1/2 times 53 squared minus 1/2 times 25 squared divided by 9.81. Okay, that should tell me the height of the cliff. Okay, so 0.5 times 53 squared, okay, minus 0.5 times 25 squared, okay, divided by 9.81. Okay, cliff's 111.31 meters tall. Okay, ringing a bell from yesterday? Is 53 meters per second pretty fast? Very fast. Okay, like that is definitely going to, destroy the car. The whole action movie trope of, cars explode all the time when they go off cliffs, even though they really don't. Okay, yeah, all of that stuff would happen. Now, on that note, as we start looking into and doing more of these physics problems, your understanding of the bounds of reality will improve, which will make watching certain types of movies more difficult. Okay? One of the most important mechanisms or devices within making movies is something called the suspension of disbelief. Okay, I'd have to make it seem just real enough that you won't think about it too much. Well, as you gain a better understanding of physics, that will be a harder and harder thing for filmmakers to do. Because, well, very often they just do things that are stupid. Like in the Fast and the Furious movie, they go into space in a car. Okay, I mean, at that point, all bets are off. No one believes that, hopefully. Okay? But I'll show you an example, okay, of one of these things where when you watch it, it's like, whoa, that's really cool, and then all of a sudden your brain kicks in, and it's like, wait a minute, okay? All right, so skydiver jumps out of a moving plane at 90 meters per second, 10,000 meters above the ground, okay? How fast will the skydiver be falling when he is 8,000 meters above the ground? Assuming he has been in free fall and not opened his parachute. Okay, let's have a look at this one here. So if we have the skydiver who jumps out of the plane, okay, we know the initial height, as they tell us it's 10,000 meters. Okay, and we know that their initial speed is 90 meters per second. Does it matter that that's horizontal and not vertical? It actually doesn't, because remember, we're talking about speed here. Kinetic energy only has to do with how fast you're going, not what direction you're going in, okay? So we've got our initial values and we've got our final values. Our final values are 8,000 meters, and we're looking for how fast is that person going when they get there. All right, so we'll start it out the same way we always do, EI equals EF. Okay, so initial potential plus initial kinetic, okay, equals final potential plus final kinetic. Okay, everybody with me so far? Okay, any of those zero in this question? No. In fact, this would be the most mathematically involved question you'd ever be asked to do. There's none of them are zero, and we have to solve for V. Okay, so on that note, we're solving for VF, which is part of the final kinetic energy, so we need to subtract the final potential over to this side. So we'll have initial potential plus initial kinetic minus final potential equals final kinetic, and now we can plug in our formulas. So M times G times H initial, okay, plus 1/2 mv initial squared, okay, minus m times g times h final equals 1/2 mv final squared. Okay, what can I do with the m's? Cancel them off. Good, because I wasn't told what the mass of the skydiver was anyway. All right, I need to get VF by itself. What do I do with the half? Divide it over the other side. Okay, so 1/2 gone from this side. That solves for VF squared. So I need to square root that. Now I can plug in my numbers. 9.81 times 10,000 meters plus 0.5 times 90 squared minus 9.81 times 8,000 meters divided by 1/2. All right, so 9.81 times 10,000 plus 0.5 times 90 squared. Okay, minus 9.81 times 8,000. Okay, divided by 1/2. Square root that number. Okay, that's fast. I wouldn't want to be falling that fast. Okay, like that is, what's his name who jumped from space and fell? Okay, the Red Bull guy. What's his name? I can't remember. Anyway, he went up on like a hot air balloon into like low Earth orbit or something like that, and then he jumped. Okay, and he fell for a long way, broke the sound barrier, the whole works. That's not the sound barrier fast, but I sure wouldn't want to hit the ground at that speed. I mean, it isn't the fall that kills you, it's the sudden stop at the bottom. Right? Okay. Everybody okay with how that one worked? So 217.57 meters per second. And you did get going pretty fast, okay, when you skydive. Now, in the real world, could you get going that fast? Probably not. Okay, in the real world, what is there that we're ignoring? Air resistance. Okay, any falling object is going to have a terminal velocity where the force of gravity pulling you down and the force of air resistance acting against you balance, and you stop accelerating. Okay? And you actually fall at your terminal velocity the rest of the way down. Terminal velocity is based a lot on shape and mass and things like that. Okay? I mean, if you had like a, something that was really aerodynamic or something like that, then it could fall faster. It's why you see skydivers, if they're doing all the aerobatic stuff, right, they'll move their arms and they can move around that way because they're just changing their air resistance, and that way they can move around, slow down, speed up, okay, do whatever they need to do. Okay. All right. You know what? We'll leave it there for today. Okay. I hope you all have a good Christmas. Okay. When we come back, we'll quickly review all this stuff, and I'll talk about efficiency, and we'll do a formal unit exam review. Okay. On the 6th, your work lab is due. On the 8th is your exam. So dates to think about, but not at least for the first week. Just take some time off and enjoy.